Factoring trinomials, part 2, ax squared plus bx plus c. At this point, we have factored out GCFs, we factored differences of squares, we factored by grouping, and we factored trinomials of the form x squared plus bx plus c. In this lesson, we're going to learn the second of the two most common types of factoring. The first one was the x squared plus bx plus c. This one, the difference is that we have a coefficient on the first x squared. For example, expressions like 2x squared plus 9x plus 10. In this lesson, we're only going to be factoring trinomials that have a coefficient on the first term. We can employ two different methods, a factor and sum table, and this one will be slightly modified from the one we had used before, or the big giant X using grouping. Okay, so just as we had before, we can have a situation where both B and C are positive. This means we're going to have all positive factors. So our method 1 is going to be a factor sum table. And again, this is a modified factor sum table. So instead of having 2 columns, we're having 3. Our first column is going to be factors of the A term. That's this one. Here's B and here's C. Our second column will be factors of the C term. And then our last column will be the sum, and we want it to equal B. So in this case, we're going to have factors of 2, and we want a sum of 5. Luckily, 2 only factors into 1 and 2, so that will make this one a little bit more simple. Now, in order to deal with this, we don't just add 1 plus 2 and 1 plus 2. That's not what works. What we need to do is similar to FOIL. We're going to multiply the first times the first and the second times the second to start. That'll give us 1 times 1, which is 1, and 2 times 2, which is 4, and that equals 5. So we got that on our first try. Now, if that one hadn't worked, we would then do the first times the last and the second times the first. And I would have gotten 1 times 2, which is 2, and 2 times 1, which is 2, which would have given me 4. Once we've completed this and we figured out which combination we want, we then need to put these together. I want to multiply 1 times 1 and 2 times 2. Well, this first set, these are our n's. So I'll have 1n and 2n. 1 needs to multiply by 1. That means I need to put it over here. 1 times 1, as if we were foiling. And 2 needs to multiply by 2, so I'll put that here. And they're both positive. And then to clear that up, we don't usually have a 1 as a coefficient ever, so I'll rewrite that. Now method 2 is to use the big giant X, but we're going to use the big giant X to convert to grouping. And so the first thing we need to do is we need to do A times C, which in this case is 2 times 2, which is 4. And then when we make our big giant X, the multiplication and the addition, this is the number that goes here, and the addition is still B. Then I find factors of 4 that will add up to 5. 2 and 2 add up to 4. 1 and 4 add up to 5. Then the next step is going to be to replace our B term with our new factors. So instead of having 2n squared plus 5n plus 2, I'm going to take this 5n out, and I'm going to replace it with 1n and 4n. And the reason I do that is because 5 is 1 plus 4, so I haven't actually changed anything. I've just turned this into a situation where I can factor it by grouping. From 2n squared and 1n, I can factor out an n. From 4n and 2, I can factor out a 2. There should be an n right there. And I get n plus 2 times 2n plus 1. And as you can see, I get the same factors, it's just a different method. And for some people, the table will be easier. For some people, the conversion will be easier. It's a matter of preference. You can use either method. So let's try another one. Again, remembering that these are both positive, so all the factors are positive. So I'll try my method 1 again. I have factors of 5, factors of 12, and I want my sum to be 19. Now, factors of 5, that's nice because there's only 2 factors, 1 and 5. But 12 actually has multiple factors. So I'm going to start with 1 and 12 and see if that will work. Again, I'll do first times first. 1 times 1 is 1. And then second times second. 5 times 12 is 60, and that will give me 61. Obviously, that's not 19. So then I'll do 1 times 12, which is 12, and 5 times 1, which is 5, and that's 17. Closer, but still not correct. When that happens, we need to try a different set of factors. Again, my factors of 5 are 1 and 5. For 12 this time, I will try 2 and 6. And I will do 1 times 2 and 5 times 6. This is 32. That's not the right setup. So I'll try 1 times 6 and 2 times 5. That gives me 6 plus 10. Again, not 19. So I have to try another set of factors. Now, luckily, so far, we've only had 1 and 5 as our first set of factors. If we had a number like 6, we would have to continue to try different combinations. So after we had gone through all of the possible combinations of 12 with 1 and 6, let's say, then we would have to go through all the possible combinations of 12 with 2 and 3. So the factor sum table can get kind of cumbersome in that way, but if it makes most sense to you, do use it. Okay, we've tried 1 and 12 and 2 and 6, so we're left with 3 and 4. 1 times 3 and 5 times 4 gives me 3 plus 20, not 19. And then I do 1 times 4 and 3 times 5, which gives me 15, and 4. I finally have my 19. So those are the factors that I'll want to use. Okay, so we're doing n's. So these are my n's. So I have 1n and I have 5n. I want my 1 to multiply by 4, so the 4 goes over here, and I want my 3 to multiply by 5. These are both pluses, and to clean it up. Okay, so let's try method 2, which is the big giant X. First, I do a times c, which is 5 times 12, which is 60. I make my x. I want to multiply to make 60, and I want to add to make 19. So I'm going to start thinking of factors of 60 that will give me a 19. 6 and 10 is 16. 2 and 30 is 32. 20 and 3 is 23. And then we can keep going through and we get 15 and 4, which will be 19. Now, another way to find these, if you can't come through all the possible combinations of things that will divide into 60, is to factor it. And then combine these. So I can say, okay, 6 and 10, 4 and 15. And I find them. After which point, I take my original terms and I replace the 19n with 15 and 4. Now when I look at this to determine which one comes first, 5 and 4 don't really have anything in common, but 5 and 15 do. So I want to put the 15 with the 5 and the 4 with the 12. Out of these two terms, I can factor a 5 and an n, and I'm left with n plus 3. Out of these two terms, I can factor 4, and I'm left with n plus 3. And I get 5n plus 4 times n plus 3. Now, I personally like this method better because it eliminates the need to try an unknown number of possible combinations. But again, we get the same answer, so whatever method you prefer is the method you should use. As before, we'll have a situation where we have b is negative and c is positive. When this happens, we have two negative factors. Okay, so I'm going to multiply two negatives together to get a positive. Now the factors that are negative are these. Since this is positive, these will still be positive factors. Okay, so using my factor sum table, I have factors of 3, factors of 4, and I want them to give me a sum equal to negative 8. 3 can be 1 and 3, and I'll try 1 and 4 for 4. 1 times 1 is 1, 3 times 4 is 12. This is not negative 8. Oh, sorry, these should be negative. What was I thinking? Still not negative 8. And then I have 1 times negative 4 and 3 times negative 1, so that gives me negative 4 plus negative 3, also not negative 8. So I'm going to have to try my other factors. Again, 1 and 3 will only factor as a 1 and 3, but 4 will factor as a negative 2 and a negative 2. So I have 1 times negative 2 and 3 times negative 2. 3 times negative 2. So I have negative 2 and negative 6. This does not, this does add up to negative 8. So this tells me I have my factor combination. These are my n's. So I have 1n and 3n. 1 needs to multiply by negative 2, and 3 also needs to multiply by negative 2. So I have n minus 2 times 3n minus 2. Using the big giant X, I do 3 times 4, which will give me 12. And I want factors of 12 that will add up to negative 8. And I quickly can come up with negative 2 and negative 6. I replace my negative 8 with the negative 6n and the negative 2n. And the reason I put the 6 with the 3 is because the 6 and a 3 have something in common. I can take out a 3n, and I'm left with n minus 2. Here I have negative 2n plus 4, so to make this a minus 2, I need to factor out a negative 2. And I get 3n minus 2 times n minus 2. Okay, for our next example, I have 6x squared minus 20x plus 6. So again, c is positive, b is negative, so these factors will be negative. And these factors will still be positive. Using my factor sum table, I have factors of 6, factors of 6, and I want a sum of negative 20. So I'll start with 1 and 6. One and 1 is 1. 6 and 6 is 36. These should be negative. That is not negative 20. If I do 1 and negative 6 and negative 6 and 1, I get negative 6 plus negative 6. This is also not negative 20. So next I'll try my next set of... Okay, now 6 has two sets of factors, 1 and 6 and 2 and 3. Now I can choose to change both and see if that will work, or I can choose to change one or the other. I'm going to keep this first column 1 and 6 and change this to negative 2 and negative 3 and see if that works. I have 1 and negative 2 and 6 and negative 3, and that gave me my negative 20. Now if that setup hadn't worked, I would have gone ahead and switched this to the 2 and 3 and tried negative 1 and negative 6, and then I would have tried 2 and 3 with negative 2 and negative 3. So I would have had to try possibly 2, 4, 6, 8 different combinations to find this match. But luckily I found it on the third. These are my x's. So I have 1x and 6x. 1 goes with negative 2, so that makes the negative 2 over here. 6 goes with negative 3, so that's there. So I have x minus 3, 6x minus 2. Method 2 requires that I multiply 6 times 6 to get 36. And I'm looking for factors of 36 that will add up to negative 20. And I know off the top of my head, 36 is 3 times 12, and that's 15. And then 2 times 18 is 20. So negative 2, negative 18. Then I take my 6x squared minus 20x plus 6, and I replace my negative 20 with 2x and 18x, both negative. From my first set, I can factor a 2 and an x. Interesting. Leaving me with x minus 1. And then from my next set, I can factor a 6. I'm going to do a negative 6, and I get 3x minus 1. Oh, I have 3. That should be a 3. You'll notice, though, that I could tell there was something wrong. I just didn't see it right away. When I pulled out my 2, I left my 3 behind. These match, so I get 2x minus 6 times 3x minus 1. Now, this did not actually match these, but it looks to be, because I had 6's, my other combination here would have worked as well. 2 times negative 1 and 3 times negative 6, and that would have given me negative 2 and negative 18. So this one actually could have factored 2 ways, which is interesting. That doesn't normally happen. But they're both correct. Okay, sometimes C is negative and B is positive. When this happens, I'm going to have one positive and one negative factor. And because B is positive, the positive one is larger. Using the factor sum table, I'm going to have factors of 2, factors of negative 9, and I want a sum of 3. 2 factors as 1 and 2. Negative 9 can be negative 1 and positive 9, or it could be positive 1 and negative 9. So we'll have to try both. So I can do 1 times 1 and 2 times 9, and that gives me negative 1 plus 18. That won't work. Now if I switch these, and let's say this was positive and this was negative, I'd get positive 1 and negative 18, which still would not work. But that's what would have happened if the signs were changed. So if you get the right numbers but the wrong signs, just switch your signs. Okay, next I try 1 times 9 and 2 times negative 1, and I get 9 plus negative 2, which is also not a 3. So now I'm going to have to try other factors of 9. Again, 2 only has 2 factors. 9 can be a 3 and a 3. One of them will be negative. So I'll try 1 times negative 3 and 2 times 3, and I will get negative 3 plus 6, which adds up to 3. So this is my correct combination. So these are my n's. So I have 1n and 2n. 1 gets multiplied by negative 3. 2 gets multiplied by positive 3. Using my big giant x conversion, I'm going to be 2 times negative 9 to give me negative 18. And I want to find factors of negative 18 that will give me a sum of 3. 2 and 9, 6 and 3. Okay, so I've got a 6 and a 3. I want one of them to be negative. Since this is positive, that makes my smaller number negative. I replace my 3n with 6n and negative 3n. From the first set, I can pull out a 2 and an n, and I'm left with n plus 3. From the next set, I can pull out a negative 3, and I'm left with n plus 3. And I get 2n minus 3 times n plus 3. Trying one more in this method style. I have factors of 6, factors of negative 49, and I want a sum equal to 7. 6 can be 1 and 6 or 2 and 3. Luckily, 49 only has 2 factors. Well, that's not true. It has 1 and 49 and 7 and negative 7. I'm going to try 7 and negative 7 first because of the fact that my sum is small. So I don't think I'm going to need to use the 49, but we never know. So I'll try 1 and 7 and 6 and negative 7, and I will get 7 minus 42. This is not 7. So then I will try 1 and negative 7 and 6 and 7, and I will get negative 7 plus 42. That also doesn't work. So next I'm going to try 2 and 3, and I'm still going to work with the 7 and the negative 7. I'll do 2 times 7 and 3 times negative 7. That will give me 14 minus 21, which is negative 7. So I don't want that particular combination. I want the other combination. So I want 2 times negative 7 and 3 times positive 7, which will give me 21 minus 14, which is positive 7. So I have my x's. So 2x and 3x. 2 needs to multiply by the negative 7. 3 needs to multiply by the positive 7. So I get 2x plus 7 times 3x minus 7. Using the big giant x. 6 times negative 49. Now this is not always the easiest method because sometimes you get these really big numbers, but still, if you like this method, it will work. So I'm looking for factors of 294 that will have a difference of 7. So this is when I'm going to make that factor tree. 294 will divide by 2, and that's going to be 2 times 147. 147 will divide by 3, so that'll be 3 times 49. And 49 is 7 times 7. And then I can try combinations of these 4 numbers. So I can do 2 times 3, which is 6, and 49. That's not 7. 21 and 14. Okay, so I know 21 and 14. I want a positive 7, so I make a negative 14. I replace my 7x with negative 14x plus 21x minus 49. 6 and 14 have a 2 in common, and they both have an x. That leaves me with 3x minus 7. 21 and 49 have a 7 in common, so that leaves me with 3x minus 7. So I get 2x plus 7 and 3x minus 7. So again, same answer. And using the factor tree really helped to narrow this down pretty quickly. For our last possibility, we can have that c is negative. So again, one positive, one negative, and then b is negative, so the negative is going to be larger. Using our factor sum table, factors of 3, factors of negative 5, and I want a sum equal to negative 2. Well, 3 only has 1 and 3, and negative 5 can have 1 and negative 5, or negative 1 and positive 5. I'm going to try 1 and negative 5 first. Okay, so I'll do 1 and 1, and 3 and negative 5, and that gives me 1 minus 15, which is not negative 2. Then I'll try 1 and negative 5, and 1 and positive 3, and that will give me negative 5 plus 3, which does equal negative 2, so this is our combination. These are p's, so I have p and 3p. 1 goes with negative 5, so the negative 5 goes in the opposite parentheses, and then 3 and 1 go together, so that 1 goes there. Using a modified big giant X, I'll do 3 times negative 5, which will give me negative 15. So I want to multiply and make negative 15, and I want to add to make negative 2. That's a 5 and a 3. I want it negative. I replace that 2p with a 3p minus 5p. The reason I chose that is the 3's in common and the 5's in common. I can pull 3p out of the first, and I'm left with p plus 1. I can pull negative 5 out of the second, and I'm left with p plus 1. And I get 3p minus 5 times p plus 1. Okay, last example. 4n squared minus 15n minus 25. I'm looking for factors of 4, factors of negative 25, and I want a sum equal to negative 15. First I'll try 1 and 4. 25 is only 5 and 5. One of them is going to be negative. So I will do 1 times negative 5 and 4 times 5, and I will get negative 5 plus 20, which will give me a positive 15. So if I switch and I do 1 times positive 5 and 4 times negative 5, I get 5 minus 20, which is negative 15. So starting with the 1 and 4 instead of the 2 and 2 really actually paid off. Found our combination rather quickly. If that hadn't worked, of course, I would have done 2 and 2 with the 5 and the negative 5. These are my n's, so I have n and 4n. N gets multiplied with the positive 5, so this is the negative 5. Using our big giant X, I'll do 4 times negative 25, which gives me negative 100. I want numbers that multiply to make negative 100 and add to make negative 15. 100 is 50 times 2, 25 times 4, 10 times 10, 5 times 20, and I want my negative. So I take my 4n squared minus 15n minus 25, and I replace negative 15n with negative 20 plus 5 4 and 20 have a 4 in common and an n, so I get n minus 5. 5 and 25 have a 5 in common, so I get n minus 5. And that gives me 4n plus 5 times n minus 5. As you can see, in every example except for that one, we got the same answer, and that one was kind of an anomaly in that there were 2 correct answers. So again, whichever method you prefer, you should use. They both work out the same way. You get the correct answer either way as long as you follow the steps correctly, and it's just a matter of preference.